All right, good afternoon, everyone. I'm going to be working on the Unit 6. This is called a quest because this is actually part 2 of Unit 6, but this is going to be the Unit 6 review video, again, part 2, that focuses primarily on polynomials and all the different things that we learned about polynomials. So the first thing you see in this first section is where it asks you to write it in standard form, then classify it by its degree and number of turns. A reminder with degree and number of turns, the number of turns is always one less than. Okay, so just keep that in mind that once you have it in standard form, you can determine the degrees. Now, the degrees by definition is the highest exponent. So you might be able to look at some of these problems right off the bat and say that the degree is 3, which means the number of turns would be 2. So you don't always have to necessarily put it in standard form to determine the degrees and number of turns. But as a reminder of standard form says you need to be putting it in highest exponent to smallest. So my highest exponent would be this negative 4x to the third. My next highest exponent would be this positive x squared. So I write plus x squared because it's positive. And then my last one, a 3x. And that would be considered standard form. In a problem like number 4, you are going to need to distribute before you can even classify or determine the degrees. So this would end up becoming an x to the 4th, x squared times x squared, x to the 4th, plus x squared times x would give us an x to the 3rd, and then plus the x squared times 1 x squared. In which case now you can see the degree is going to be 4, and that means your number of turns would be 3. And that's standard form. And you'll find that the word standard form comes up in other sections. So you at least want to be familiar with the concept of standard form being highest exponent to smallest exponent. Now the next section here, it is tempting to start kind of thinking to yourself, oh, well, what if I wrote it in standard form? Let me FOIL this, do that. But actually in this section, they're asking you to determine the zeros, which means rather than having it in standard form, we actually want it in factored form, factored form. And factored form means that basically we have it in these groupings. And from these groupings, we can look at this and say, what value of x can I plug in that will result in a 0? Well, over here with this x plus 4, if I were to plug in a negative 4 plus 4 would give me 0. The x out in front is all by itself, so what could I plug in? A 0. Now, another thing that it asks you to address is this idea of multiplicities. And multiplicities mean, is any of your answers that you just got happening more than once? In which case, this second answer here is squared, which means x equaling negative 4 is actually happening twice. Or for the first one, we could say x equals negative 8, but because it's cubed, we need 3 of them. Okay. And again, multiplicities come into play when we get to graphing. You do want to be able to recognize when there is a double root versus a single root. Okay. Now in example 8, 9, just 8 and 9, I believe. Yes. 8 and 9, these are not currently in factored form. So in order to determine the zeros, we do need to put these in factored form. So to put these in factored form, you want to first check to see if there's any greatest common factors, GCFs. So is there anything that all of these numbers or variables share? Well, the one thing that they share is they all at least have an x squared in them. So let's say that I pull out an x squared from each of these. If I pull an x squared out of the first one, that leaves me with x squared. If I pull an x squared out of the second one, that leaves me with 10x. And if I pull an x squared out of the last one, that leaves me with 25. Okay, now the next part focuses in on this piece and asking ourselves, well, ultimately we need to factor it. So we know a lot of different strategies for factoring. One of the most popular is the X method, where we say what number multiplies to 25 but adds to negative 10. So going through all of our numbers, I'm thinking 5 and 5 would get me to 25, but 5 and 5 is not going to get me to a negative 10. So what about a negative 5 and a negative 5? That means my factored form, we're going to have that x squared still out in front, but this piece is going to become an x minus 5 and an x minus 5, which means now I'm ready to determine the zeros, and I'm going to get x equals 0. I should get it twice because it is squared. I'll get an x equals positive 5, and also another x equals positive 5. So we end up having two double roots, one at 0 and one at 5. Onward to the next section. So the next section says, write each of these functions, there's the magical word again, standard form. So standard form, again, meaning write it from highest exponent to smallest exponent. But looking at 11 and 12, these need to be factored first. And these are pretty exciting problems to factor because they actually have 3 sections. So let me walk you through how to factor one of these problems. So in order to factor one of these problems, we actually just want to focus on one piece at a time. So if I focus on the first piece, we can factor this. So I'm going to get an x squared plus 3x minus 1x and also a minus 3. So again, I'm really just focusing on that first piece and ignoring the second piece. If I combine like terms, I'm at an x squared. I can combine these two to become positive 2x and a minus 3. So these two pieces up here just became this x squared plus 2x minus 3. Now I'm ready to bring down the next piece, the 3x minus 1. And from this factored form, I'm going to clean this up a little bit so we can get rid of some of the distractions. Now what we're going to be looking at is to basically still FOIL these problems. And what we want to do is we want this x squared to be multiplied by the 3x and the x squared to be multiplied by the negative 1. That would give me a 3x to the third minus x squared. Then I need to do it again with the 2x. So I'm going to take 2x. Sorry, let me clean it up a little bit. We're going to take this 2x times 3x, 2x times 1. So that's going to give me a plus 6x squared minus 2x. And then last but not least, I need to do the negative 3 times the 3x and the negative 3 times 1. That would give me a negative 9x plus 3. So at this point, we've now FOILed everything. Everything in here was multiplied together, and then everything over there was multiplied by the 3x minus 1. And now it's just a matter of combining our like terms, 3x to the third. Let's see, we can combine those. That would become positive 5x squared, negative 11x, and a plus 3. And that is in standard form because we are going highest exponent to smallest. So now you can give number 12 a whirl, doing the exact same thing. Start out by factoring just 2 pieces at a time. So factor these, get a new piece, and then factor it with the 3 minus x. On the next form, this is where it gets a little exciting. This one says, write the polynomial function in standard form. So let's ignore the idea of standard form for a second and just focus on the idea that it gave us the answers. So this is going to be like the reverse of what you saw up here with 5, 6, and 7. So they're giving us the answers and asking us to write it in factored form. Once it's in factored form, we can then turn it to standard form. So going through this, think in reverse and think to yourself, if I got x equals 0, what would that look like on the inside? It'd probably look like x plus 0, or some might even argue that it would just be x because x plus 0 is 0. Same thing with the second 0, that's going to be another x. The minus 3, well, again, think about it this way. Let me give you one more scroll backwards here. Boop. Notice how up here, it started as a plus 4, but my answer was a minus 4. So usually your answer is the opposite of what we actually have in factored form. So down here, my answer was negative 3, which means I must start it out with a plus 3. Or the positive 2, I must have started out with a negative 2. Because again, these values up here are what could get plugged in down here that would result in a 0. So if I took the negative 3 and I plugged it in, 0. If I took the positive 2 and I plugged it in, 0. So now what I have as my answer in factored form would be an x times x, which by the way would become x squared, times that x plus 3 times the x minus 2. So again, just looking ahead, I'm not going to do 14 for you, but it's usually just going to be the opposite of each of these. So you have a positive 5, inside it would be a negative 5. You have a negative 1, inside it's going to be a positive 1. You have a positive 1, inside it's going to be a negative 1. So it's always kind of the opposite. And once you get it to this form right here, the standard form, then you're just going to actually do very similar to what you did in 11 and 12. You need to write it in standard form, which includes some form of foiling. Some of you will choose to distribute the x squared and then foil. Some of you will choose to foil first, and then after you foiled it, multiply it by an x squared. It really is just a preference. So working this out in my head a little bit, if you foiled first, this is what you'd get, and then you could go ahead and distribute that x squared. All right. Onward to the next section. The next section says, write each of these functions in factored form. So we actually already talked about this section a little bit up here in problem 8, where you basically want to pull out your GCF and then do the X method. So down here, I'm going to let you guys practice that a little bit more. Look for that GCF, greatest common factor. Once you pull out your greatest common factor, it's most likely going to be solvable by the X method. Now, number 7, I give you the hint that this is going to be long division. So keeping in mind that this is going to be long division, we can set this up, and I'm going to quickly walk you through one of these examples, but you might find that you want to pause it throughout and kind of figure out where some of the numbers are going or coming from. So on the outside, I have the x plus 4, and then on the inside, I'm going to have my polynomial, 5x minus 12. Now to do long division, as a reminder, we are always trying to get the first variable to match the first variable. Whatever happens to the second piece, like the plus 4, is what it is. So I need to ask myself, x times what gives me an x to the third? So this is where I'd put my x squared at the top. In which case, now what I want to be thinking about is if I took this x squared and I times it by x, that's going to give me an x to the third. If I take this x squared and I times it by 4, that's going to give me a plus 4x squared. And once you have that set up, now we're ready to subtract. Keep in mind, we are subtracting the entire thing. It might be easy if you just write it this way, and then just keep a conscious eye on that subtraction. So over here, x to the third minus x to the third, they cancel out. Boom, boom. And then over here, 6x squared minus a 4x squared gives me 2x squared. And now we're ready to carry down our next number, plus 5x. From there, we repeat the process. So x times what gets me to a 2x squared. So I'm actually going to times it by a 2x this time. In which case, when I times it by a 2x times x gives me a 2x squared. 2x times 4 gives me a positive 8x. And again, I'm ready to subtract. So I'm going to go ahead and subtract this. Boop. When I go through my subtraction, again, 2x squared minus 2x cancels out. 5x, again, minus 8x would give us a negative 3x. Carry down our last number, negative 12. And then last but not least, again, looking for that negative 3x. So x times what gives me a negative 3x? Should times it by a negative 3. If I times that by a negative 3, it should give me a negative 3x. And again, negative 3 times 4 would give me a negative 12. Subtract all of this. So if I have a negative 3 minus a negative would actually become plus, so they cancel out. Negative 12 minus a negative 12, well, negative negative becomes plus, and again, they cancel out, leaving me with 0. If you get 0, that's awesome. That means it is indeed a factor. And I can actually write my answer in factored form as x plus 4 times an x squared plus 2x minus 3. And so if I was looking to fully factor this, because this is great, it's going in the direction of factoring, but if I wanted to fully factor this piece could actually be factored. So I could factor this by setting up our little x and saying what number multiplies to a negative 3 but adds to 2? we'd probably get ourselves a +3 and a -1, in which case our final answer, our fully factored answer, would have this x plus 4, because we determined that it is a factor. That's what the 0 meant. And then the second piece would become x +3 and x -1. And that would be fully factored and ready to get us the zeros. It doesn't ask you for the zeros, but we could easily find them and get ourselves a -4, a -3, and a +1. And that is the benefit of long division. So it kind of seems silly at the beginning, like, why are we doing this process? But once you've done this process, you have a very quick, easy problem to work with that you can indeed factor. Now, going on to the last page here, the last page has some graphing involved. So I'm going to go through the graphing fairly quickly, but you may need to go back to your notes. I remind you guys that with factoring, the key is being able to recall all the different rules. There's just so many different rules when it comes to graphing. Okay, now I'm going to do problem 18 with you guys. But before I do 18, I want to point some things out in 20 and 21. These two problems are currently not in factored form, right? So before you even do 20 and 21, you will need to factor them first, which is why we've had so many sections, 15, 16, 17, 8, 9. We've had so many sections at this point in the review packet that require you to factor. So 20 and 21, you are going to have to factor first, and then you'll be ready to graph. So going into graphing, first thing we want is the x-intercepts, also known as the zeros. So they're looking to say what values of x will result in zeros. Going through this problem, the first one we would get -2. Keep in mind it will be twice, so I'm going to write it twice. It will play a role in the graphing. Then the second one, we're going to get +1, and then the last one, +5. Again, if you need to go back to the zeros from up above, go for it. Now, these zeros, also known as the x-intercepts, can go on the x-axis. So let me put a dot at -2, +1, and +5. Okay, x-intercepts. Next up, the y-intercept. And basically, I'm going to erase this now because we're done with this. Save myself some space. The y-intercept, so I'm going to write over here, y-intercept, is whenever the x value is 0. So this is different than the zeros, the x-intercepts. This one is the y-intercept, where we're actually going to plug in 0 wherever we see x. Plug in a 0. And we're going to see what we get when we plug in a 0. So if I plug in a 0, I'm going to get 0 plus 2, which is 2. It is being squared. Times 0 minus 1 is a -1. Times 0 minus 5 is a -5. So this would give me ultimately 4 times +5, giving me 20. So my y-intercept is at 0, 20. So I'm actually going to put this up here. I'm just going to label it as 0, 20 for now, and that should be enough for us. So there's the y-intercept. Next, we need to consider if there are any double roots. And I'm just going down the line. You don't have to do it in this order. But any double roots, I do like to point out that we had a double root right here at x equals -2. So you don't have to write this in. I'm just making it clear for you guys. This will, in the end, be a double root. But that could mean that it's coming down from the top and bouncing off. It could be coming from the bottom and bouncing off. But we don't really know what that looks like at this point. So we'll come back to that double root here in a moment. Next up is the end behaviors. And again, the end behaviors might be something you have to refer back to in your notes. But as a little reminder, the degree determines the left side. Okay, so degree determines the left side. And whether that left side, I apologize, hold on. I did this backwards. Hold on, sorry. Backtrack. So we will have the leading coefficient. Okay, I was right. Sorry, I had them backwards in my head for a second. But no, I had it right. Okay, so leading coefficient. I'm just going to write leading coefficient and degree. Those are the two things that you need in order to determine end behavior. Now, the leading coefficient determines the right side, And as I said previously and then erased, degree determines the left side. And those are just rules you have to memorize, okay? So again, if you need to go back in your notes and relook at those, that's fine. For the right side, we're asking ourselves, is it positive or is it negative? Because if the leading coefficient is positive, that means that my graph will be going up. If my leading coefficient is negative, that means my graph will be going down. The degree, on the other hand, is a little more annoying. The degree is a matter of even versus odd. And if it's even, that means that all we know about the end roots are that they're going the same direction. Okay, we don't know if that means up, we don't know if that means down, but we do know they'll be going the same direction. Odd stands for opposite. So again, we don't know if that means up or down. All we know is that it's going to be the opposite direction as the right side, which means, in short, we have to do the right side first, and then we can determine the left side. So we have our right side over here and our left side. So looking at our problem, what exactly is our leading coefficient? Our leading coefficient in this circumstance, the number way out in front, is going to be a 1. Okay. In standard form, you might be able to see that leading coefficient a little bit easier, being like a -1 or a +1. But in factored form, it is usually just the number that's way out in front of everything. So in 18, the problem that we're working on, our leading coefficient is a +1, which means my right side is going to be going up. So I'm going to come over here and draw an up arrow from the right side. Again, make sure that it's pointing not only straight up, but up and to the right, henceforth the right side. So point to the upper right-hand corner. Now, all we have to do is start weaving through our 3 points. Keep in mind that every single one of these points represents a point that we need to cross. So looking at this first point, we already have this side covered, which means we need to cross it and come to the other side. We were in the positive sides of our graph, and now we've transitioned to our negatives. Now go to your next point. Again, we're in the negatives and we're ready to transition to the positives. So I come up here to the positives. Now don't forget about that Y-intercept. It's kind of hard to see up here because I made it green, but we do need to go through that Y-intercept and come back down. And now we're ready to hit this point here, but wait, we cannot forget, this is a double root, which means when I hit that double root, I'm actually going to bounce back up, and there's my graph. Now you might be thinking, well, wait, Ms. Maurer, we didn't talk about the degree and the left side. But if we look at our degree, again, keep in mind degree is your highest exponent. In factored form like this, we can actually just count the x's. So I have 2 here, 3, 4. So my degree is actually a 4 for this problem because that's how many x's I have. I have the x plus 2, the x plus 2, that's 2, then 3, then 4. So we have 4, which is an even number, which means my 2 end behaviors should be going the same direction. And sure enough, check that out, they are in fact going the same direction. So you can do the end behaviors up front and kind of determine the 2 end behaviors and then start weaving in and out. Or you can start with the right side, do your whole graph. You saw me do the whole graph. As long as you don't forget about double roots, you'll be fine. So start weaving through all of your points. And then at the very end, look at your end behaviors on the left side and determine if it does in fact match. So again, we went through that process at the very end saying, what's my degree? My degree is 4, and therefore they should be going the same direction, and sure enough, they are. So everything went well. If I look at the second one, my degree, again, count the x's, 1, 2, 3, 4. My degree is 4. So again, we don't know if that means up or down, but we do know that they're going to be going the same direction. So once you figure out the right side, the left will be doing the same. Now, in the second one, I do just want to point out that none of these are double roots. So none of this problem should bounce. Every single one of these points, you should go right through the dot and out to the other side. You only bounce when it's a double root. 20 and 21, I don't know if there's any double roots. You're going to have to factor it first. And once it's factored, like we did in the other sections, this was factoring, those two are factoring, you got a couple factoring up here. But once these two problems are factored, then you can go ahead and graph. So hopefully this helps. Again, a lot of these rules are just a matter of do you have them memorized? But that hopefully helps point you in the right direction as far as your studying goes. Again, go back to your notes if you need more help. Good luck.